Or you can if you want. I just find it tedious if you do tree diagram, but if you're happy to do it. If you want to do it. Yeah, exactly. All right, 6 to 10, 12, 13, 14. Well, good? All right, here we go. Let's start off. Factorial. Factorial and permutations. First, we're going to understand what factorial is. Factorial notation basically provides a convenient way of expressing products, consecutive natural numbers. Yes, Monica. You need my help. Yes, you can. I'll be right back. But you guys are going to tell me this.
Take your time, sir. Take your time. Don't rush. Take your time.
I'm going to take my time.
Yeah, take your time. See you to practice. Let's go.
Oh yeah.
Yeah. Oh, my mom and a friend. And my mom's friend and her daughter. That's all. Oh my god, this guy. I'm sorry, Mom. Yeah, look at mine. Oh my god. Three. Okay, sure. Actually, you can buy this from there.
I'm back. Here we go. Factorial notation. Now this might look intimidating. The exclamation mark right here means that it's factorial. Factorial basically means you're going to be multiplying consecutively until you get to 1. Okay, so for example, if you write 3 with an exclamation mark, what that basically means is, or we say 3 factorial, but what that means is you're saying 3, this is equivalent to, oh, wait, why is this, oh, it's so out of, I guess I'll go back to this. Equals to 3 times 2 times 1. Okay, so you're consecutively multiplying by the 1 before that. Okay, so 3, the next one before that, 2, and the one before 2 is 1. That's what 3 factorial is. This is what the symbol's trying to say. So whatever that factorial number you're saying is, that's going to be multiplied to the 1 less, and then multiplied by the 1 less than that, and the 1 less than that until you get to 1. Does that make sense? Okay, so when I say, let's say 10 factorial, what that means is I'm going to be multiplying down to 10, down to 9, down to 8, down to 7, down to 6, until I get to 2 times 1. Does that make sense? So when we're talking about factorial, that's what the exclamation mark means. Yes? Yep. You're not going to see it. Yeah, I know. I was trying to write on the screen, but I think it's not calibrated. Yeah, I don't know why. It's a bit off. Yeah, it's a bit off. I don't know. I don't know why that happened. I have to restart the whole thing to get that working. So you're going to look at the white screen. Okay? Now that we understand what factorial is, okay? Factorial is you're multiplying consecutively until you get to 1. Now notice the 2 notations, both of them are actually the same. See this one, I'm saying n factorial is whatever that number is, times 2 the number before that. And then times 2 numbers before that. And then times 3 numbers before this number until you get to 1, right? But you can also say, since this is n, you can also write n minus 1 factorial. Because n minus 1 factorial just basically means times this. This is n minus 1, times that by the 1 less than that. And then times that by 1 less than that, and it carries on. Okay, so this is n minus 1, the one before that is n minus 2, the one before that is n minus 3, and it carries on. So these two are exactly the same, but one's nice, this one's nice, because it only has n. It doesn't have this infinite sort of sequence. Okay, this you can use, you don't need to require the n beforehand, you just need n, and you can solve it. Okay, so these two formulas are exactly the same, and their key is doing something like this. Okay? So, let's have a look at these two. Let me get you to look at it. 3 factorial means 3 times 2 times 1. We know the answer is 6. Okay? If we look at 50 factorial, it feels like it's going to be, it's going to be tedious to solve 50 times 49 times 48 times 47 times 46 until you get to 1. But what you need to also understand is 50 factorial is the same thing as saying, I'm going to write it here, 50 times 29 times 48 times 47, it carries on, right? But then why can't I just write the top line, the numerator, why don't I rewrite that as 50 times 49 factorial? Because 49 factorial is the same thing as saying 49 times 48 times 47 times 46. True? Yep. And that's what this line is saying. Okay, so take n times the one before that factorial. That's what this is. Okay? If I divide that by now 49 factorial, this is actually easier to solve. Because 49 factorial divided by 49 factorial is the same thing as saying times 49 times 48 times 47. And what we know is 49 divided by 49 is 1. 48 divided by 48 is 1. 47 divided by 47 is 1. And it carries on until you get to 1 over 1. So that nicely and conveniently simplifies down to 50 times 1 over 1. Does that make sense? Okay, so factorial means you're multiplying consecutively until you get back down to 1. And we know that we can also write it as n factorial as n, taking the first term times the second term factorial. Okay. Let's try this one then. You'll go 10 factorial divided by 2 over, or 2 factorial times 8 factorial. So what is this equal to? I want you to simplify that for me. Don't need to lose your exercise book. So we go. What's 10 factorial divided by 2 factorial times 8 factorial? Yep. For writing that you guys acquired. Because it picks up the first noise it can hear and it calibrates it. So if I'm standing over there and you guys are talking about it, it'll calibrate to that side. So you hear me whispering in the back. Because if you're not talking, then it'll pick up my voice and it calibrates. Let's check our answers. 10 factorial.
I was like, yeah, okay, that's right. Why don't you understand? What's going on? You're explaining to me. So why do you understand?
You forgot 4.
Oh, doesn't matter. Comes forward. There you go. Okay, and then we've got 2 factorial, which conveniently is cancels that out. And then we've got 8 factorial, 8 factorial, which actually might as well keep the 2 factorial there. So 8 factorial, we know that 8 factorial and all the 8s here will cancel out to be 1. Technically, you've got 10 times 9. 90 on the numerator, and 2 factorial just means 2 times 1, which means 90 divided by 2 gives me 45. Hands up, you got 45. Excellent, good. Okay? Is that easy? Factorials. Yeah? Let's move on to why are we learning factorials? Okay, so now we understand what factorials are. How is that important? Now, I'll show you how it's important to understanding this concept. Modulus.
Oh, modulus. What was that?
A permutation is an ordered arrangement of a collection of objects. Now it's a fancy way of trying to understand what they're trying to say there. All they're really trying to say is if you have a number of objects, I want to arrange them such that the order does matter. Order meaning which one comes first and which one comes second does matter. Okay, each arrangement is the same. Is different, and it's not the same. So, for example, using a tree diagram, they're saying use a tree diagram to list all the permutations, means different ways, where the letters of the word cat can be written. Now, logically, you can write cat. That's one way of writing cat. So you have C coming first, A coming next, and then T coming next. Okay, that's one order. When order doesn't matter, that means even if you have A, C, T, technically it's the same group. Okay, and an example of that is like saying, if I asked you to pick a team of 3, okay, and you chose 3 people, whether you chose, let's say, Jamie, Michael, and Rose, whether you chose Jamie first, Michael second, and Rose third, it doesn't matter if you then chose Rose, and then Michael, and then Jamie. That order doesn't change. So even though the order is different, the team is still the same. So that's when order doesn't matter. Permutation means that the order does matter. So whether I chose Jamie first, and then Michael, and then Rose, why does it matter? Maybe because, why did I choose Jamie first? Was it because I favored him? Was I more biased to him? I'm like, no, I'm going to choose him first. Does it mean when I chose him first, it means he's first ranked, second ranked, third ranked? That's when arrangements or orders matter. Does that make sense? The difference between permutations and having an arrangement or order matters, or order doesn't matter. So in that case, when you choose a team, it doesn't matter who you choose first. That's when order doesn't matter. But when order does matter, so if I said first place, second place, third place, it does matter who I choose first. Yeah?
Permutation does or doesn't?
It does matter.
Does.
So this would mean that you have Jamie choosing Jamie first does matter. Okay. All right. Now using a tree diagram to list all the possible ways, what you don't want to do, because remember this is counting methods, what you don't want to do is sit there and write CAT, ACT, and then CTA, and write all possible solutions and then count them. That takes too long. There has to be another way. Now, using a tree diagram at least gives you a method to solving that. So here's the method. And from the method, we're going to use a technique, okay? So let's think about this. The first option, okay, if you think about it, in the first option, if you were to choose a letter, okay, there are 3 letters, there's C, A, and T, then there are 3 options that you can choose as the first letter. Okay, so there's 3 options, and you can only choose one of the 3. Okay, so you've got C, A, T. So you had 3 options. Then, in your second letter that you chose, after you chose one, remember you can't repeat it. Okay, it's like me choosing Jamie, I can't choose Jamie again, I've chosen once already. Yeah? So I've had 3 options. I had Rose, Michael, and Jamie. I chose Jamie. So that means I'm now left with either Michael or Rose. So it's the same thing. If you chose C, you're only left with an A or a T. So if you chose an A, then you're only left with a T. So that's CAT. That's one way. Alright? Then you chose CT. If you chose T in the next one, then that means you only got A. But the point is, in the second option, you only have 2. So you had 3, you chose 1, there's only 2 left. Yeah? And if out of the 2, you chose 1 again, then there's only 1 left at the end. Now this is very similar to what we were talking about yesterday in multiplication principle. We said that if every 3 you have 2, and every 2 you have 1, we know that we can work it all out by saying 3 times 2 times 1. True? Okay? And because if it's 3 times 2 times 1, that conveniently is what we were just learning just now. 3 factorial is actually helping you to find number of permutations, where order does matter. Does that make sense? Okay, so if I had to change that situation, I said CATE, now you don't have to draw a tree diagram, we know there's 4 options there, and I want to see how many ways I can rearrange them. It would logically then be 4 factorial. Because after you choose the first letter, there's only 3 left. After you choose the second letter, there's only 2 left. If you choose the second letter, there's only 1 left. So it's 4 by 3 by 2 by 1. Okay? And so that means 4 factorial, 4 times 3 times 2 times 1 is what? 4 times 3 times 2 times 1, that's 24. So without drawing a tree diagram already, I've just taught you a method so that you can figure out by counting how many different ways can I arrange the 4 letters C-A-T-E where the order does matter. Okay? Order does matter. Which one I choose first does matter. Okay? How's that feel? That makes sense? So now we can see the link, what a factorial is, how we can simplify factorials, how that leads to permutations. Cool? Permutations is the number of ways you can reorder something where order does matter. Okay? Alright. Now, so number of permutations n objects is n factorial. Now, This is one of the things I think someone asked me at some point, I can't remember who in this class, but someone asked me, why is 0 factorial equal to 1? And I said that eventually I'll show you, and there's 3 proofs to this. Okay. Oh, 3 ways of thinking about it to prove it. Now, 0 factorial. We agreed that factorial means n times the previous number, right? So let's go with this understanding. It's n times n minus 1 factorial. True? Now you can, with mathematical proofs, some of it can be, especially with this one, this is very similar to your index laws, where you say 3 to the power of 0 equals 1, or a to the power of 0 equals 1. See, there's actually no understanding what it actually is. So a to the power of 0, I don't know what that is. But if I said a to the power of 3, I know what that is. That means I've got a times a times a. But if I said a to the power of 0, I can't actually physically tell you what it is. It's the same thing with 0 factorial. We can't physically tell you what it is, but we know what it equals to. Okay? Now, we only know that by inspection or inference or reference. Okay, however you want to say it. So n factorial, so this is true. Let's look at a pattern. Okay, so we have a pattern. Let's say we know that 3 factorial, which was 3 times 3 minus 1. True? So 3 times 3 minus 1 actually works out to be 3 times 2 times 1. Yeah? So that works. But then, and we knew that 2 factorial meant 2 times 2 minus 1, which ends up being 2 times 1. True? So then if I go to now 1 factorial by following the same pattern, we already know beforehand, even before we start using this formula, we knew that 1 factorial is 1. It's 1. Yeah, 1 times 1 is 1. So we already knew this is true. Now we want to follow, because by definition we said... Yeah?
But no, 1 multiplied by 1 minus 1 is 0. 1 multiplied by 0 is 0.
No.
1 equals.
What you just said was true. We don't know. It wasn't 0. We didn't know what that was. We don't know what this was.
Does that mean 1 factorial equals 0 factorial?
Yes, because they're both equal to 1. They're both equal to 1. So we only know it by pattern.
I don't like that.
But you just said it yourself. You just said, if we went with that. Now, that is one proof. Yeah. Yeah.
Sorry.
Yeah.
Sorry.
Yeah.
Hold on.
Yeah.
Give her a second. Zeros. But why is there a factorial? There, like, do you go into negative numbers? But then can't you do
That's a good question. I'll show you the second proof. What we don't. Let's go. No. Hold on that thought. Hold on that thought. Let's go with the second proof now. Let's go with the second proof.
So we say we don't go into negative numbers, meaning that 0 is the last number.
That's a
Meaning
fair
0 to the factorial is not a thing.
No, I love what you're saying, because that works into the second proof. Because the second proof will fix what you're asking. Okay, so let's have a look. Let's have a look at the second proof as of what you're saying. Like, why are we to say that 0 is the last one? We don't know that. Why can't we have negative 1 factorial? Why can't we have negative 2 factorial? That doesn't make sense. So let's work out with the second proof, okay? So let's go with this idea.
I'm so angry.
Let's go with this. We understand that 5 factorial means 5 times 4 times 3 times 2 times 1. Right? That's what we mean when we say
Okay, but
factorial.
why though?
But this is just how we write it.
Okay.
It's like saying 3 times 3 times 3. Someone just said, hey, why don't we write it as... It's just easy. We need it away. Yeah? Okay. So instead of writing 5 times 4 times 2 times 1, we write 5 factorial. Okay, so we went with that method. And we know the answer is 120. But here's the thing. If we write now 4 factorial, now this part here might be confusing here. 5 factorial over 5 is the same thing as 4 factorial. Why is that true? Because you got 5 factorial means 5 times 4 times 3 times 2 times 1. If you divide by 5, technically that is still the same as 4 factorial. Okay, so now we've got a pattern. We got 4 factorial is 5 factorial divided by 5. True?
So then 4 factorial divided by 5.
No, you're right. 4 factorial is equal to 24. Then 3 factorial following the same pattern should be 4 factorial divided by 4. Agree? But 4 factorial is 24. 24 divided by 4, 6. Okay, which makes sense because then you have 3 times 2 times 1, it does actually equal 6, so it's true. Okay, so let's go with the second one then. So that means 2 factorial should be what?
Is this going to be like a joke?
No. 3 factorial over 3, true? So 3 factorial over 3 would mean 6 divided by 3, which is 2. So that makes sense. 2 times 1 is 2, that's true. Now, here we go. Let's go with 1 factorial. 1 factorial would then simply mean 2 factorial divided by 2, true? And 2 factorial is 2, so 2 divided by 2 is 1. So we agree that 1 factorial equals 1.
We agree that in this instance, 1 factorial is equal to 1.
Okay, we agree.
But,
Wait.
so are we saying that negative numbers...
Wait, no, wait. We haven't got into that. So when we got to 0 factorial, here we go. 0 factorial would then mean 1 factorial divided by 1, true? But we had 1 factorial is equal to 1, so that means this is 1 divided by 1, which equals 1. So now we agree that 0 factorial equals 1, true? According to this pattern. But why can't we have negative 1 factorial? Let's have a look. If we did negative 1 factorial by the same pattern, we should have 0 factorial divided by 0. 0 factorial equals 1. But 1 divided by 0 is what? Not defined. So that is why in your textbooks they'll say this rule will only work if n is greater than 0. Because anything before that is undefined. If you're asking why does it have to be integers, yes, it doesn't have to be. There's actually a formula, which that's way beyond my scope now, that you can work half factorial. I don't know how to do that. Okay? You can search that yourself. I'm sure it's somewhere on YouTube. But for now, we're just working n as an integer. How do we feel? Good? Okay, so that solves that idea. Alternatively, if you didn't like all that proof, then logically, if factorial is your permutations, right? Permutations means the number of ways you can arrange things. Now, if you think about it, if you had 2 objects, so let's say 2 objects, like this, okay? If I had 2 objects and I said, how many different ways can I arrange it? This is one way, true? And the only other way I can have is that. So for 2 factorial, I mean two objects, the only number of ways I can arrange it was 2, which makes sense. 2 factorial was 2, so that makes sense. If I had 1 object, how many different ways can I rearrange it? 1. Now this is on a philosophical point in terms of the logic here. If I had no objects, how many different ways can I arrange it so that I have no objects?
But if you can arrange nothing into something, then you can arrange nothing.
Yes, and this is why I'm saying it's on a philosophical point. We're saying the only way to arrange nothing, this is the only way. So what you can see is what it is. Okay? But at the end of the day, I'm just trying to say 0 factorial is equal to 1. Don't question it. Okay? All right. Let's go into this. Let's go into this. Oh, did you want to see it again?
Yes.
Woo.
Can you do it again?
Yeah. Oh, and then, yeah. All right, now let's have a look at this. How many ways can 6 different books, now that we know what factorial is, we know what a permutation is, let's think about this. How many ways can 6 different books be arranged on a shelf? So you have 6 different items. It's like saying A, B, C, D, E, F. Is that it, right? I think it's F. It'll be 6 factorial. Okay, and it makes sense because in the first position, because remember the order matters, in the first position, how many different books did I have? I had 6. And I chose one of them. Now if I chose one, then the second one I only have 5 left.
The only logical way is alphabetically go 5.
Okay, that's why it makes sense you say 6 factorial. Next one. What about this one? How many 4-digit numbers can be formed using the digits 1, 2, 3, and 4 if they cannot be repeated? So let's think about this. How many 4-digit numbers can be formed using the digits 1, 2, 3, and 4 if they cannot be repeated? 4 factorial. Makes sense, because that's what we were saying. You don't repeat it. If I chose Jamie, I can't choose Jamie again, so it's not repeated. So the first one makes sense, it's 4 factorial. What if it's repeated? Yeah. See, well, a lot of the times, a lot of students don't realize this, but see, in the first one, it made sense. In the second one, you ask the same question. You say, in the first position, how many options did I have? I had 4. But in the second one, I still have 4 because I can repeat it. So it's 4 by 4 by 4, which makes sense. It is 4 to the power 4, which makes 256. Does that make sense? So when you're dealing with these problems, don't try to think of it as a formula. Try to think of it, what are you doing? What are you asking? Okay, how many different ways? So one's repeated, one's not. Factorial, and when you're repeated, well, how many options do you have? Yeah, just think of it that way. Yeah? Now, all right, let's go into now the last part that I really wanted to teach. Okay, so we understood 2 things so far, and I want to finalize that last one before we finish. First one was what factorials meant. Factorials then led to permutations. Permutations meant that how many different ways can you arrange something where the order does matter. Okay, who do you choose first matters. Now, sometimes we have, like let's say in this class I've got 23 students in this class. But let's say I want to choose the 3 people. Okay, I only want to choose 3 people. So there's 23, but I want to choose 3. Then now this makes it a bit more difficult because how many different ways can I arrange or choose people where I can choose Rose first, then I choose Michael, and then I choose Dan. Okay? How many? I mean, it might not have been in that order. It could have been Daniel first, Michael, and then Scarlett. How many different ways can I arrange that? We don't want to sit here and start arranging every groups of 3. Okay? And it takes too long. Yeah? Well, it will take too long to do. Yeah, probably too long to do. Okay? So, how do we do this? And this is what the question is asking. Permutation is where you choose the order, but if you have more objects than the amount of people you choose. Okay, so if I had 23 kids, but I'm choosing only 3. If it was 23 and I chose 23, that's a bit easier. Yeah? In this case, you have permutations of n objects taken at r at a time. So I'm taking 3 at a time. Out of 23, I'm choosing 3 at a time. The question is, how do you solve it, right? So here we go. I want you to imagine this. If there is a small town where there are very few cars, and each car is to have a license plate. But the license plate can only have 4 digits, where the 4 digits cannot be repeated. So you got 1, 5, 3, and 9, just as an example, right? They're not repeated, and in terms of the digits that you have in our mathematical system, we only have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So those are our digits. I want to make a 4-digit plate for this town. The question is, how many different number plates can this town have? Now I've got 10 digits to choose from, but I want to make combinations or arrangements of 4 only. Okay? So logically, if we were to do this, think of it this way. So again, don't try to think about formulas or anything. Just think about it. I've got four positions for the 4 digits. In my first position, how many options can I choose? 10. I have 10 digits, so I can choose 10 possible numbers or digits. Yeah? And then after I choose 1, remember I said it cannot be repeated. So if it's not repeated, how many options do I have left? 9. And then? 8. And then 7. So technically, 10 times 9 times 8 times 7 will give me 3,628,800. Okay, so this is the number of ways or number of plates I could possibly have. Okay, different type of combinations. The order does matter. Okay. Unless I did it wrong.
You did it wrong.
I did it wrong?
5,040.
5,040. I must have done it to an extra power or something.
Yeah, that is so true.
Now, copy this part down. This is the notation. Well, when you write a superscript, is what we were saying, on the left-hand side superscript, the P means permutations. If you have 10 items, so how many items are you choosing, or how many items are available, and how many of those are you choosing at a time? This is known as NPR. Normally, R represents the number of times you choose, how many of those items you choose at a time, and N is the number of items available. Okay, so in our case, we're saying we've got 10 items available, and I'm choosing 4 at a time. This is our answer. It was 10 times 9 times 8 times 7. So what they wanted to do was we wanted to figure out a generalization. What if I had 10 to 2? Or what if it was 10p3 or 10p7? There has to be a way to figure this out. And so here's the pattern. They're saying, let's try to use, because 10 times 9 times 8 times 7 is very similar to our factorial system is just missing 6 times 5 times 4 times 3 times 2 times 1. True? So what we're going to write is we're going to write this. Well, why don't we put it in? Why don't we put it colored in red, because this is what we don't have. We're going to times by 6 times 5 times 4 times 3 times 2 times 1. But if you put it on, that means you have to divide it. Okay? Because that means that it doesn't really exist. Because you want a formula. You want to generalize this. Okay? So to generalize it, we can now say, well, that means the numerator now can technically be 10 factorial. Agreed? And the denominator can actually be 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial. Do we agree with that? Yes. Okay? So this first line is equivalent to this line. But we still want to see a relationship between 10 to the 4 and 10 to the 6. And what we can see is that 10 take away 4 gives you that 6. So what we can do now, we can say, oh, wait a minute. Why don't I write the 6 as 10 take away 4 factorial? This nicely leads into this concept that 6 factorial, that still equals to what 10p4 is. But if you write it as 10 factorial divided by 10 take away 4, which really, if you put in letters now, if this is m, this is n. If this is r, there'll be n minus r. And this is your formula, logically, to generalize if you wanted to find out a number of items you have. So the example I gave to you before, I said there was 23 students in my class, okay? And I want to find the number of ways where I can choose someone and the order does matter, and I'm choosing 3 people. Okay, then that will be equivalent to 23 factorial divided by 23 take away 3 factorial. Now you have a method. Now you've got your calculator, you can figure that out. It's possible to figure out. And technically, 23 minus 3 factorial is the same thing as saying 23 times 22 times 21 times 20 factorial, all the way down to 23 take away 3 is 20 factorial, and what you can already see, 20 factorial divided by 20 factorial cancels out. Your answer is really just 23 times 2 times 21. And that will tell you the number of ways that we can arrange this classroom right now where I choose 3, and we figure out how many ways that we would have to do to figure that out. Does that make sense? So let's look at the 3 skills that we've learned. We've done factorials, we've done permutations, okay? And then we've now done permutations where you choose a certain amount at a time. Does that sort of ring? But what I want you to do is don't try to memorize these rules. Okay, as you're doing these questions, I want you to think of it as that. Because this is logical. So you didn't have to do all these rules to get there. You just did 10 times 9 times 8 times 7. And that was very logical. This is just a formula when it gets more difficult to do. Yeah? But logically, this is where it comes from. All right. Let's put your understanding to a test. Let's try an example. Let's try this one. Using the letters A, B, C, D, and E, so I got 1, 2, 3, 4, 5, without repetition, how many different 2-letter arrangements are there? Okay? So think about it, you've got 5 letters to choose from, without repetition, so I don't want repetition. Once you use an A, then you can't use an A again. How many different ways can I do that? And if you were to do it, how would you do it? What's the idea for A? What would you do for A? Fantastic. This is the same thing as saying 5, you've got 5 items, you want to find the arrangements where order doesn't matter and you're only choosing 2. Now according to what you learned just now, that was 5 factorial over 5 take away 2 factorial. You can do it that way, or think about it logically, you only got 2 spaces to choose. There are 5 items. 5. In the first space, there's 5 different letters that you can choose. Once you choose that letter, how many letters do I have left? So how many different ways? 5 times 4. Now let's check this one. This is 5 factorial, 5 times 4 times 3 times 2 times 1. And this is 3 factorial, which means 3 times 2 times 1. That's 5 times 4, which is true. But can you see the difference between the two in terms of understanding? You can use that rule, but I don't want you to just be rule-driven. Try to think of like, why do I have that rule? And really, it's all you're really doing. and that helps it. So if you answer the second question now, see if you think about it, 6 runners compete in a race, and how many ways can you get gold, silver, or bronze? And how many different ways? There's 6 runners, there's 6 people, and you're choosing 3 spots. And there's only 3 spots, but you can't repeat 2 golds, you can't have 2 silvers. You've got 1 gold, 1 silver, 1 bronze. So technically, logically, you can go with this one, you can go 6P3, or you can say there are 3 positions for gold. So for gold, you got 6 people to choose from. But after you choose 1, there's only 5 left. After you choose 5, there's only 4 left. So logically, it'll be 30 times 4, 120. So what I'm trying to do? I'm trying to say, yes, you can do it this way, but logically is what I want you to be able to understand. And you can use both. How do we feel? That's exercise 7B. Permutations, factorial, permutations where you choose an amount. The order doesn't matter. Cool. Hopefully I've described it well enough. Other than that, what's the time? Oh, perfect. I will